Okay, it works-ish. And that's a horrible picture. Okay, I'm told that there's a setting for video on demand. I do not know how that works, but I am recording the streams here. I'm going to post them to YouTube. So people are mentioning that. I don't know how video on demand works, but that will be something I figure out at some point. Okay, so how are we doing? 1 to 5. How do we feel right now? That's not going to help. Let's see. I need to ask in chat here. Pi, yes. Stephanie always feels pi. There we go. Oh, 1 to 5. How do we feel? Okay. So, I just discovered something. I need to do 2 sets of notes because this has all the notes that I did from last time. Okay, so first we need to go over the quiz, correct? So let's do that first. And then I will do this here at page. And this will be 20. Oops, wrong one. This will be 20, 20, 03, 23, R2. And then we want to bring you to the new class. Okay, so last time we went over maxes and mins. Last time was, I'm so sad. I don't get to see you all again in person. Last time we went over, min max, Fermat stationary point theorem, and we went over the extreme value theorem. And we had a quiz for today, so let's look at the quiz very quickly. So the quiz looked like this. There it goes. And then I forgot to print it out and make notes on it. So I just wrote for the last class on the thing. So we will talk about it there if everyone's okay. And I can't see your reactions because now we're live. So on the internet instead of in person. Also, please remember that first of all, the geeky hand glove, that's to stop. I discovered this last time. If I don't have the geeky hand glove on and I move on the page, it does this, which is very annoying. It still does that sometimes, but if I have the geeky hand glove on, now when I move on the page, it doesn't always do it. So I have the geeky, that's hence the geeky glove that I'm wearing. So there's the explanation for that. The other thing is that I have discovered is that the laptop has a tendency, the tablet that I'm using, same tablet you saw in class, has a tendency to overheat. I have not solved that problem. I have a backup display, which is the X Pen, but it doesn't work. So yeah, they also do it for that, but I'm just using it because it keeps it from activating everything. So there's the geeky setup. Other things about the geeky setup, you can tell that I'm in front of the camera. Hi, because I have a green screen behind me, which my cat loves to get into, and when he gets into it, you might see the background start to shimmer. So if you see the background shimmering and suddenly, destroying the illusion of me being in front of the screen, that's because my cat is playing in the screen. He loves to do that. Anyway, so we have a quiz. And somewhere I have a cursor. Wrong mouse. Okay, so we have this beautiful quiz. Let's just go ahead and talk about it. So did anyone have any issues getting on Gradescope and getting Gradescope to work? Just anyone that has an issue, type in the thing. There was also a question last time. Am I going to do uh, still allow retakes? The answer is yes. I have not solved the problems yet. So retakes are down at least for the week. But as soon as I solve the problems, it will involve Gradescope. It will probably involve Proctorio. As soon as I solve those problems, then retakes will be back up. Any questions about that? Okay. But I haven't gotten that far yet. Anyway, so back to the thing. Let's talk about the quiz. So the quiz, the first question, of course, was, Gradescope. Some people are typing in the thing. Because we are live on Twitch, I will be reading questions that you post in the chat. So I will be reading the questions you post in chat. However, I'm not going to be saying your names because privacy issues. It's on Twitch. Anyone can look on Twitch. So privacy issues. I'm not going to be saying your name when I answer a question, but I am going to be repeating the questions. Anyway, so the extreme value theorem. There are a couple different ways to say it. This is one way. Let f be a function. If f is continuous on AB, then f has both a minimum or a maximum. And you can write in here, you can write the following, you can write this global. It's already doing it. Global min and max, etc. Any questions about that one? You can also say this fancy thing with the set. This set has both a min and a max. And here is, remember that this is a set of y values. Thank you, Gracie. My cat also likes to treat the mouse as if it was a mouse. Fine. Okay, so remember that this right here is a set of y values. And that set has both a min and a max. Are there any questions about this problem? Okay, 1 to 5, how do we feel about what this thing is actually saying? How do we feel about the intermediate value theorem, 1 to 5? You can vote here. You click on the little numbers and it votes. I'm sorry, the extreme value theorem, not the intermediate value theorem. Okay. So anyway, it's talking about a set of y values and etc. Okay. So the next theorem we have is Fermat's stationary point theorem. And there's two ways to say it. The first is to say if f is differentiable at x, and if f has a local extremity at x, then f prime of x equals 0. It is also correct to say the following. It is also correct to say if f has a local extrema at x, then either f prime of x equals 0 or f prime of x does not exist. How do we feel about the fact that those are two equivalent statements? How do we feel about the fact that these things are equivalent? Okay. All right. Any questions about that? Okay. So let's go ahead and go down this more. This last question, find the absolute min and the absolute max for x cubed on -1 and 2. Now, there was a typo on the first version of this test where I had -1, 1. I was thinking -1, 2 when I wrote it, but I wrote -1, 1. If you turned it in with -1, 1, that's fine. There are two versions of the key. One, which, well, if you turned it in with the original, and one if you turned it in with a typo fix. So if you turned it in with the wrong question, don't worry about it. That's fine. Anyway, so the procedure for doing this, the first thing I'm going to do is check my endpoints. Now, you don't have to do it in this order, but I find that if I check my endpoints first, it stops me from making the mistake where I sub into the wrong function. So I just right away, I get this thing, I check my endpoints. Your results may vary on whether or not you keep making that mistake. I keep making that mistake. I make that mistake all the time. And for that reason, I do my endpoints first to kind of at least try to check myself on it. Any questions about that? Okay. Then, so I check my endpoints, and I get that my endpoints are -1. Uh, my checkpoints, I check -1, and I get this, and I check -2, and I get I'm sorry, I checked +2 and I wind up with 8. And these are the y values that are associated with -1 and -2 in the x space. How do we feel about that? 1 to 5. Let's see, that's there. How do we feel about that? What I did was I just checked the endpoints. How do we feel about it 1 to 5? Okay, now there's a question about if 0 is a local min. No, it isn't here. We'll get to this in just a moment. Um, 0 is actually an inflection point or nothing in the case of maximum minimum. It's neither. And we'll get to what that means in just a minute. Now, I want to find my critical x values. These are the values where either the derivative is 0 or it doesn't exist. Now, this thing is a polynomial, so its derivative exists everywhere. Let me get rid of this. There we go. This thing's a polynomial, so its derivative exists everywhere. Therefore, I only really need to check where its derivative is 0. So I take the derivative, I set it equal to 0, and I wind up with x equals 0 as a critical x. Now, the next thing I'm going to do is I'm going to plug my critical x's back into the original equation. And I wind up with a y value of 0. So now I've got 3 values. I've got 3 suspects. I've got -1, 8, and 0. And the question is, of those numbers, -1, 8, and 0, those are my y values. What's the biggest and what's the smallest? And the smallest is -1, and the maximum is y equals 8. And I want the y values, not the x values. How do we feel about that 1 to 5? I really like this 1 to 5 thing, though. I get to ask you 1 to 5 in the chat. It's beautiful. It's beautiful. By the way, if you're still in general chat, come on down here to Calc 11 a.m. chat, 0321. So if you're watching this right now on general chat, switch your text chat over to 11 a.m. chat 03. Okay, any questions about that? All right. So the next thing we want to do, so that's the end of the problem. So there was this question about 0 being a local min or a local max. And if I take x cubed and I take its graph looks something, like this, except not quite as horrible. Hold on, there is a math function on this link. Let me see if I can get it to work. It's something I haven't gotten to work yet. Let's see, math. Graph in 2D. Cool. How do I give it the... Anyone know how to make this, let's see. F of x equals x cubed. Let's see. Hey, cool. Hey, check it out. It worked. So there is y equals x cubed, which is the graph we're talking about. Now, here you can see that if wait, I can send this to background, right? Yes. Oops. All this needs to go. Nope, we don't want that to happen. Can any of you all see this stuff happening? I'm sorry, you guys can't see the graph, and I don't know why. That is psychotic. Um, okay. Uh, okay, you guys can't see anything I'm doing. It's not that you can't see the graph, it's that you can't see anything that's happening on my tablet. So let's see if we can't call this bad boy off and make it work again. Um, great. So apparently the source has completely failed. Great. I'm sorry about this. Okay. Well, we need technical support, and I can't get it for this. Let's see. Well, thank you. Someone in chat is saying that stuff happens. It's okay. Hey, this is my first time pulling this off, so, well, it's my first time trying. Obviously, I'm not pulling it off. Uh, let's see if I remove you. Yes, I want to remove this. So I want to go just the board, and I want to remove you there too. Off with your head. Now, it's not Twitch. So people are saying I've never used Twitch. It's not Twitch, it's OBS. And the problem is that I have a laptop. The problem is that I have a tablet PC that I want to write on because this thing that I bought to write on the screen directly doesn't work very well. So I have this tablet PC that I want to write on, and I want to transmit using the main PC because that's where all the videos work, okay? And what's happening is that the connection between the tablet and the PC that I'm broadcasting from has completely failed. Uh, hmm. All right. Well, all right. Backup plan. Ha ha ha. Okay. So we got the backup plan up. I can't write right now, but I can at least talk and show the screen. Okay. So anyway, if you do this, yay, that's up. Okay, so if you do this on here, you wind up with this graph here, and if you zoom in here, which I can't do because I'm not on my screen, so we can go to backup plan. So if I zoom in here, something interesting is happening at 0. Okay, here, notice here on the left of 0 that the slopes are all positive. Is everyone on board with that? And at the right of 0, all of the slopes are positive. So how do we feel about the fact that the slopes of this graph are always positive, 1 to 5? Okay, so the slopes are always positive. But notice here that to the left on this graph, let's get rid of this, to the left of 0 here, my slopes, they're always positive, but they're getting less positive and less positive and less positive and less positive and less positive, okay? So this function, the change in the change, the second derivative is getting shallower and shallower and shallower and shallower and shallower. But then I go back again, and then the slopes get positive and positive and positive and more positive again. Okay? So here my derivative is decreasing, and here my derivative is increasing. How do you feel about that 1 to 5? Okay, so I have a situation where I went from slopes that were decreasing in steepness to slopes that were increasing in steepness. So, um, let's look at another situation that we get. So this is what's known as an inflection point, and that's sort of what we want to talk about today. We want to talk about inflection points. Okay, so let's bring up. Let's go back to the notes for today and talk about these. Uh oh. Uh-oh, uh-oh, uh-oh. Hmm. Any luck? Nope, tablet's gone. Okay, well, we can't use the tablet. Um, so let's talk about this. So I'm actually going to have to cheat and just use my notes from last time. So let's talk about something that's, in the news right now. And that's what happens about the change in the change. So let's take a situation where I've got one infected person, and every day that person infects, every infected person infects another person. Okay? Which thing do you want me to repeat? Okay. So I've got a question in here. He's typing it up. Um, so each day we've got a person who infects another person. Uh, uh, okay. I don't know why, again, this thing's not working, but it's making me very upset. Please work. Okay, so here's what's frustrating. It says it's working, okay, and then it's not working, and it's extremely frustrating. And I'm sorry you guys are having this thing now, but I think it has to do with the thing overheating. Anyway, um, what we're going to do is we're going to turn this off. Oh, and now it works. Okay. Yes. Okay. So what I said about the derivative was that graph. Wait for it. Ha 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 ha. It works again. Okay. So what I was saying was that the graph Perfecto. Okay, so what I was saying about this was that the graph was that the slope of the derivative was changing. So, just a second, let me recenter the screen like it's supposed to be. There it is. Okay. So what I was saying was that the derivative of this thing, come on. What I was saying was that at x equals 0, okay. So what I was saying was that the change in the slope changed at x equals 0. All right. So let's go back, and I'm sorry I'm going to be running like way over time because of this technology issue. But um, let's see, class. Okay. So let's suppose that every infected person infects infects one non-infected person. So recall this function. Okay, I've got on day 1, I've got one infected person. On day 2, that one infected person infects another person. On day 3, now I've got 2 infected people, and they infect 2 more people. On day 4, I've got 4 infected people, each infecting one other person. So now I've got 8 infected people, and so on and so on and so forth. So by day 11, I have over 1,000 infected people. Is this relevant to our lives right now? Now, so the question is, what's going on here? What does this curve look like? So this function, of course, is f of x equals 2 to the x. So if I take the derivative of this, okay, if I take the derivative of this, I wind up with ln of 2 times 2 to the x, which is always positive. So when I look at this function, I always expect the function to be increasing. Because if the first derivative is positive, it tells me that the thing is increasing. So let's go over here and let's look at what that means. So if I go over here to this one, and I get rid of this window because that's not what we're talking about anymore, and I bring up this window, and let's look at this function 2 to the x. Now, this function 2 to the x, here I am starting at one person, here after the end of day 2, right? So at day, I've infected 2 people, and after day 1, I've infected 2 people, and so on and so forth. And it becomes very clear that very early on, before day 10, or at day 11, I'm reaching, look at this function, 1,000. There's 1,000. So everyone understand what happens with this function. It's accelerating extremely quickly. So not only is the first derivative positive, right? It's always increasing. But the first derivative of ln of x is always positive as well. But look at what happens here. Here I'm just scaling by the y-axis. So I'm flattening it out by scaling over on the y-axis. Not only is it positive, not only is the function increasing, but its rate of increase is increasing. This function is accelerating. So I take the second derivative of this function. I take the second derivative of this function, and look what happens. I get something that winds up being this thing here. And that thing is always positive. ln of 2 times ln of 2, so ln of 2 squared, times 2 to the x. So for every x, the second derivative is positive. So what that says is that not only is the function increasing, but its rate of increase is increasing. Now let's compare that to the derivative of ln of x. If I take d over dx, so if I take the derivative of ln of x, right, I'm going to wind up with 1 over x, okay? So what does that mean? If x is positive, the derivative is positive, right? So if x is greater than 0, d over the derivative so this function is always increasing. Um, Now, what happens when I take the second derivative of this? What is the second derivative going to look like? Yippee. The question is still an open one. What does the second derivative look like? Yeah. So someone answered in chat finally. So the second derivative equals negative 1 over x squared. And that blinking, I think, is happening because the thing is overheating again. That's my hypothesis anyway. Let's see. If I take an ice pack and cool it, do you think this will work, or is this a really bad idea? Who wants to, say it? Let's see if we can't cool it off with an ice pack. Okay, so yeah, I know, I just did. Make sure it isn't wet. I love this one. Probably it's a bad idea, but I would do it anyway. Okay. And by the way, I love all the emotes that are happening in the thing. Okay, so f of x equals this, negative 1 over x squared. And negative 1 over x squared is less than 0 when x is greater than 0. Is everyone on board with that? So um, because of that, you get this idea that the graph of that function is decreasing as we go on. I'm sorry, the graph is always increasing, but its rate of increase is decreasing. In other words, its second derivative is negative. The change in the change is negative. Now, let's compare that let's talk about these other functions. This function right here, this original one, this x squared, it just blows up. Whereas log slows down. It keeps getting bigger, but it slows down. Of course, this right here as a model talking about epidemiology things, this is not so great of a model because there's a problem with using this function as a model for epidemiology. And that is that there's not an unlimited pool of people that can get sick. Okay? And then there's a question in chat, if f double prime of x equals 0, does that mean f of x must be linear across that interval? Yes, that's exactly what it means. Okay, so let's look at this. Let's look at this function here. This is right now what we were saying. What we were saying here was that, what we were saying, let's move this back, is that this was happening if every person infected another person. Now, this is not a realistic model for a disease because there's only so many people that can get sick. So what we want is something more like this. Now, this function here has that same kind of property that 2 to the x did at the very beginning, right? I can make it, let me speed it up so you can see that. Okay, so this has that same idea of 2 to the x, right? I'm blowing up exponentially at the beginning. Does everyone see that? But what happens so let's say this thing's out of 100. So let's say this is the percent of the population that's infected. So if I go up here, at some point, I start running out of people to infect. So at some point, the curve starts slowing down. And as you can see this, somewhere around y equals 60%, the tangent lines start running above the curve. In other words, the graph is still increasing, but the rate of increase gets slower and slower and slower. And eventually, of course, when 100% of the population are infected, the thing kind of flattens out and you get no more increase. How do we feel about that, 1 to 5? Okay, so now this is the second derivative, okay, that we're talking about here. Now, in the news a lot, there's been this idea of bending down the curve. All these people are saying that they want to bend the curve. And what they're not saying, that they want to flatten the curve. And when they say that, they're not actually saying that they want fewer people to get infected, although that is, they want that too. What they're saying is, when they say they want to flatten the curve, what they're saying is they want to stretch out the length of time over which people get infected. The idea being that, this is kind of total number of people who got the infection, not total number of people who were infected at a given time. And the idea is that if I can flatten out this curve, I won't overwhelm my health system, because at any given time, the number of people that are currently sick, again, this is the number of people total who have been infected. Now, we assume that, after a few days, some people get well, and unfortunately, some people don't get well. But either way, they're no longer in the hospital system. So the idea of flattening out the curve is that it takes longer and longer to happen. That's a side note on this lecture. That's what they're talking about. But to get back at what we want to solve for the place where this curve, right? We want to solve for this place where the curve stops getting steeper and starts getting shallower again. And that's called the inflection point, okay? So let's do a function that's not quite as big of a pain in the ass to play with, okay? Let's play with a different function. Let's play with the function f of x equals x cubed minus 3, minus x squared. And let's play with it on a very, very small interval. Is everyone on board with this kind of idea? Okay. So I've got people that say on fire. I've got people in this other chat that's saying it's so interesting to look at the emote chat room. Okay. So uh, let's ask ourselves a couple questions about this function. Okay. So let's look at this function and let's ask ourselves. So our function f of x equals x cubed minus x squared. It's blinking. It's going to blink again and again and again and again and again, and there's nothing I seem to be able to do about it. But the thing is cool now. The ice pack did work to cool it off. Now, whether or not that stops the thing from doing what it's doing is another question. Okay. So what I want to do is I want to find the min, max, local min, and local max, and all inflection points. And I hope nobody gets a seizure from the fact that it keeps blinking in and out like that. Okay, are there any questions about this? Okay, so this is the thing. I want to find out where this thing is happening. So let's flip back to our graph of this thing. And if we look at our graphs, and let's consider the interval -1 to 2. Okay, so let's consider that interval there. Nope, that didn't work. Okay, so here's the connection between the first and the second derivative, the first derivative here. Oops, that's the wrong screen. So where the derivative is 0, okay, where that green line is the first derivative. Now, where the first derivative is 0, that is where I'm going to look for minimums and maximums. So here is the first derivative. Here the first derivative is 0. That means I'm going to look for a minimum or maximum there. Here the first derivative is 0. So I'm going to look for a min and a max at x equals 0. Is everyone on board with that? 1 to 5, how do we feel about that? That connection between the first derivative and the minimums and the maximums. Okay. I'm at the same time that I'm talking, I'm also trying to get the OBS thing to work again on the screen. Okay, so I've talked about here where this first derivative is 0. Where I have now, look at this original function. Oops, not there. There. Look at this original function. You can see here that the function goes, here the tangent lines are running above the curve, here they're running below the curve. So right here, my function is decreasing over this entire realm. Does everyone see that? Here the function is decreasing. Not there. Not there. There the function is decreasing. But look what happens here. Somewhere around here, the function is decreasing, but the rate of decrease, the amount that the function is decreasing slows and then stops. And now the function, while still decreasing, the tangent lines start getting shallower and shallower and shallower. In other words, my rate of decrease decreases. So what I'm looking for there is something called a an inflection point. I'm looking for the place at which these things change. So if I take the derivative, look what happens at the derivative here. If I have an inflection point here, I'm going to look for the places where the derivative has minimums and maximums, because that's the inflection point. So let's go back to the other one. So by the way, the definition of an inflection point, how do we feel about what we're talking about, what the definition of an inflection point is? Okay. Let's just write out the definition. I seem to be losing people. Are these people that I've lost in the stream because I keep having technical issues and they no longer want to watch me have technical issues? Which is, perfectly understandable. Okay, so let's do that. Let's just write out the definition of an inflection point. So if I change from concave up to concave down, or the other way around, okay, that's where my graph has an inflection point. Are we all on board with that? Yeah. So someone said in chat it's the part where something changes, right? Yes. It's the part where the derivative goes from increasing to decreasing, or vice versa. In other words, if I look back at my other source, if I look back at my graph, here I went, here the slopes are decreasing, right? But here, look at these slopes. Here they're getting steeper and steeper negative, and here they're getting less steep negative, okay? So here they're getting steeper and steeper, and here they're getting flatter and flatter. So somewhere in here, the graph changed from the slopes going from getting more and more negative to getting less and less negative. Okay, so the graph went from concave down. Here this graph is concave down, and here this graph is concave up. Indeed, if I throw a modifier on this, oops, not there. If I do that, oh, that you can really see dramatically. That's not as dramatic as I want it to be there. So I can actually show this a little bit more if I do this. So if I change this function a little bit, I can actually see where that happens. Do you see how here I've got concave down and here I've got concave up? Here I've got a down, here I've got an up. And the first derivative goes from increasing to decreasing, right? And yes, so in chat is an excellent comment about what exactly is going on here. Any questions about that? So how do we feel about this thing that we're trying to find, 1 to 5? Okay. So, but as is being said by someone in chat, if I look at the derivative, here, that's what I'm looking for. Here, the derivatives are decreasing. They're all negative, right? The derivative is negative here. All the way from here to here, the derivative is negative. But here, the derivative is decreasing, which means that these slopes are getting steeper and steeper in the negative direction. And here, the derivative is increasing, which means they're getting flatter and flatter since they're negative. Are we all on board with that? So, how do I solve this? Well, if I want to solve these questions, let's see. Let's go back to the tablet. So, if I want to solve this question, what do? I need to find the place where the minimums and maximums, where I have minimums and maximums of my derivative. So let's do that. Let's solve this problem. Let's find the places where I have a min, max, local min, and local max, and all inflection points of this problem. Are we on board with this? Okay. So I'm almost out of time. So I'll finish this problem, and then that'll be it. So the first thing I'm going to do is I'm going to take the first derivative. Well, no, the first thing I'm going to do is I'm going to check my endpoints. And my endpoints, so this was on -1 to 2. So let's see, endpoints. I've got f prime, f of, not f prime, f of -1 equals what? Equals -1 cubed minus -1 squared, which equals -1 minus -1 squared, which is just 1. And f of 2 equals 2 cubed minus 2 squared, which equals 8 minus 4, which equals 4. And now I'm going to take the first derivative and set it equal to 0. So are we all on board with that bit? Now I take the first derivative. And what do I get? All right, so I take the first derivative and I set it equal to 0. Is everyone on board with that? Now, I take the first derivative, I set it equal to 0, and that's going to mean I have to factor this, right? How do I factor this? X comes out, and I get what's left? 3x minus 2, which implies that x equals 0 from this. And what about that one? That means that x equals 2 over 3. So now I plug this back into the original function. And what do I get? Yes, I get negative 4 over 27. How do we feel about that, 1 to 5? Okay. So now we have enough information to answer the question for global maxes, right? What are my y values? My y values are now 4, negative 2, negative 4 over 27, and 0. That means that my global min is y equals negative 2. My global max is y equals 4. Now, what about local mins and local maxes? Okay, so how do I answer that question? I'm still looking at the same place, right? Fermat's theorem says that I'm going to suspect these things. My suspect points are 0 and 2/3. Okay. Now, if we recall from the graph, we're going to find out that 0 has a local max, and uh, um, uh, this is a negative 2/3. Why is f of okay, so there's a question about whether why is f of 2/3 negative. The answer is because if I cube something that's less than 1, I wind up with a smaller number. It's same thing squaring it. Okay, but what I wind up with is that 2/3 squared is going to be bigger than 2/3 cubed. So when I subtract the one from the other, I wind up with a negative number. How do you feel about that? So how does everybody feel about that fact, 1 to 5? If I square a, if I square something, if I take something to a power that is less than 1, I actually make it smaller, right? So like 1/4. So when I take the power, this is a side note. Okay, so yes, so the point of checking the critical values is to find out where these local, where these extrema are. Because remember, according to Fermat's theorem, uh, if I have a local min or a local max, the derivative is going to be 0. So as you can see here, if I look at this, here I've got a local min and I've got a local max. I've got a local max here and a local min here. And if you see this green line, this line is my derivative. Notice how the derivative is 0 at those points. Okay. Let's come back here over to this one and talk about this again. So I've got local min and local maxes. How do I check to whether or not they're local min or max? Let's hold on to that question for a moment and let's go to the next bit, which is finding where the inflection points are. So now I'm going to take the double derivative. Okay? So f double prime of x is what here? Oh, low latency is on. There's a question for me to turn on low latency. It already is on. There's also super low latency, but that doesn't work. Advanced. Yeah. So low latency is already on, and it doesn't work. And Twitch does not have a super low latency. Oh, yes. Okay, sorry. You're talking about the people who didn't do it. I thought I turned it on by default. And now I don't know how to do that. Okay, so check to see if low latency. Anyway, to come back to this, I have the derivative. Now, I want to find out where the second derivative. I want to find out where the derivative has minimums and maximums. Okay, remember that. So I'm looking at this thing. Okay, and by the way, there can be functions where the derivative has a min or max, where the function doesn't have an inflection point there. But that's when you have like things like f of x equals x to the fourth, where, let me show you what that looks like. So there can be exceptions where you have things like f of x equals x to the fourth. So if I look at x to the fourth here, right, this thing right here has a global min at, it has a min or a max. It has it right here. But as you can see, there's no inflection point there. Even though the derivative is 0, the second derivative is 0. Here the derivative would not have a min or a max there. Here the derivative would actually have an inflection point. So you can get situations, I'm sorry, not where, you can get situations where the derivative is 0. There's no inflection point there. You can have a min or a max in the derivative. I'm misspeaking. There are places where the derivative is 0, where the second derivative is 0, but I don't have an inflection point. But I can't have one if I don't have a min or a max there. So what I'm going to do is I'm going to take the, looking at this function again, I have its derivative, not that function. I screwed up that function, didn't I? Oh well. Okay, so what I'm going to do is I'm going to take this, I'm going to set it equal to 0. So I've got f double prime of x equals 0, which equals 6x minus 2, which implies what? Well, that implies that 2 equals 6x, which implies that 1 equals 3x, which implies that x equals 1 over 3. Okay, so I suspect now, how do I tell? Okay, well, if the first derivative, if the second derivative is positive, that means that my function is concave up. And if my second derivative is negative, my function is concave down. So what I'd want to do is I want to look at this, okay? What's going on here? Do I have a min and a max? Well, let's ask the question. At x equals 1/3, what is happening in the first derivative? How do we feel about this idea? What I did was just took the second derivative and set it equal to 0. Oops, wrong button. How do we feel about that 1 to 5? I'm already 7 minutes over, but I did start 7 minutes late, which is, of course, bad. Okay. Excellent. Okay. So that makes sense. So what I'm going to do is I suspect an inflection point at x equals 1/3. Okay. Well, let's look at what's going on here. Around 1/3, this is 0, correct? Now, let's go just to the left of 1/3 and ask what's going on with f prime. Or let's ask what's going on with f double prime. So what is a number to the left of 1/3? I want a number to the left of 1/3 where I haven't crossed another potential inflection point. Well, 0 is a number to left of 1/3, isn't it? Let's throw in 0. And give me a number that's right of 1/3 that doesn't pass another inflection point. On 1. And then let's ask the question, does the concavity of the function change? So what is f double prime of 0? Okay, so does the concavity change? Does this change in my change? The answer is yes, right? To the left of 1/3, my derivative is negative. My first derivative is decreasing. And to the right, my first derivative is increasing, which means f itself is concave down to the left and concave down to the left, and I just said it was concave up. And it's concave. Yep, there it goes. Okay, so, and it's concave down to the left and concave up to the right. So yes, there is an inflection point at x equals 1/3. Okay. So, yes, the second derivative tells you the concavity of the Fourier function. How do we feel about this, 1 to 5? Okay. All right. So it's clear that I need to spend some more time on this. Obviously, I need to fix the technical issues that are causing these problems. So what I want to do is what we're going to do is, and I will be posting these notes as well. But what I want to do is I want to go on Wednesday, I want to talk about proofs by contradiction. And we need to talk about Rolle's theorem on Wednesday. And then peer leading on Friday, you're going to talk about the mean value theorem. Then on Monday, we're probably going to come back to this subject and redo it again. These are kind of the critical things. The first thing, to set the derivative equal to 0, define mins and maxes. That's the main part of the section. The next part of the main part of the section is this stuff. And then we'll do some proofs. We'll do some proofs by contradiction, which are always fun. We'll prove that the square root of 2 is irrational. That's kind of cool. And then we will prove Rolle's theorem, and from Rolle's theorem, we'll prove the mean value theorem. And then you'll play with these things on Friday, and then we'll come back and talk about this some more because this is important. Okay, so I've gone way over time. I do have office hours in 3 minutes. Give me just a little bit longer because I need to go set this thing back up. And you can ask me questions. Anything else for today? And yes, videos will get posted on YouTube as soon as I have a chance to do it. Why are you all in voice chat? The idea was that you could that I could chat with you at the beginning of class, and that's why we were all in voice chat. But I don't know why everybody's hanging out in voice chat afterward because the streaming is kind of one way. Any other questions? How do you tell the inflection point just from looking at concavity? With the first derivative, you look at where it equals 0, but how do you calculate the exact values instead of uh, just looking at concavity? The inflection points are places where the concavity changes. So you calculate, or they're places where the first derivative has mins and maxes. So for that, you calculate, you do the exact same procedure you do for the first derivative, except not, for the original function, except now you apply it to the first derivative. So you're looking for the local extrema of the first derivative. Does that answer your question? Again, I will go back over this stuff again. Okay, I'm now about to be late for office hours. So thank you all, and I will see you all during office hours or next Wednesday, if not. Bye bye.